Hi everyone, this is Mrs. G, and today we're going to talk about geometric sequences. So I have a quick warm up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. So we know a sub 14 is negative 23 fourths, a sub 39 is negative 73 fourths. So you could use those two pieces of information to set up a system to help you find your d value and your a sub 1 value, which gives you this explicit rule. And you can check your work by plugging in n for 39 or n for 55 and see if you get the correct term. So today we're going to focus on a new type of sequence, which is called a geometric sequence. So geometric sequence is a sequence with a common ratio, meaning that to get to the next term, you are multiplying by the same value. So this is a little different from arithmetic. So remember, arithmetic sequences have common differences, meaning you're adding the same number to get to the next value. Here, we're multiplying by the same number to get to the next value. And if the sequence is decreasing, that just means you're multiplying by a fraction that's less than 1. So we can create an explicit rule or a recursive rule for these types of sequences. So the explicit rule kind of has a formula. It's just going to be a sub n equals a sub 1, which remember means our first term, times r, which is that common ratio, to the power of n minus 1. And remember, the explicit rule describes each individual term in reference to n, which is the relative position of the term. Now, we could also do a recursive rule, which, remember, describes each term in reference to a term before it. So we do a sub n equals a sub n minus 1, which just means the term before times r, your common ratio. So you just take each previous term, multiply it by r, and that should give you the next term. And again, for the recursive rule, we do need to define a sub 1 because we do need a starting place if we're always referring to each term in terms of the term before. Okay, so let's see if we can look at a geometric sequence and create both an explicit and a recursive rule for it. And then we're going to find the 8th term of this sequence. So here we have negative 3, 9, negative 27, 81. So you can probably see what our common ratio is. We're multiplying by negative 3 to get to each successive term. However, if you're ever having a hard time finding the common ratio, you can simply take any term and divide it by the term before. So that gives us negative 3. So our common ratio is negative 3, and our first term, a sub 1, is also negative 3. So we're just going to plug that into our formula to find we'll start with the explicit rule. So a sub 1, or a sub n equals a sub 1 times r, which is negative 3, to the power of n minus 1. Now in this case, we can actually simplify this a little bit more. We can multiply these two terms because they have the same base. So remember, when you are multiplying two terms that have the same base, you're going to add the exponents. So the base is going to stay the same. So we have negative 3. And then here, we're going to add up the exponents. 1 plus n minus 1 is just n. So this is our explicit rule. Now let's do our recursive rule. So a sub n equals a sub n minus 1, which is the term before it, times our r value, which is negative 3. So it's negative 3 times a sub n minus 1. And we do need to define that first term because we need a starting point. So this is our recursive rule. And now we need to find the 8th term of the sequence. So when we're trying to find a term within the sequence, the explicit rule is going to be much more useful because for the recursive rule, to find the 8th term, we need to know the 7th term. And to find the 7th term, we need the 6th term, so on and so forth. So that's why explicit rules are nice because you can jump straight to whatever term you're looking for. So to find the 8th term, you simply replace n with 8. So we're going to have negative 3 to the power of 8. So that means our 8th term is 6,561. All right, let's try one more together. So we're going to find both explicit and recursive rules, and then we're going to find the 10th term. So let's look for that common ratio. So you can see here that our numbers are getting smaller. So that means that our common ratio is going to be a fraction that's less than 1. And it's really like we're dividing by 3. So if you're dividing by 3, just think of it as multiplying by 1/3. So our common ratio is 1/3. And a sub 1 is 45, the first term of our sequence. So we can make our explicit rule. So a sub 1 times r to the power of n minus 1. Now, in this case, our bases are not the same, so we actually cannot multiply these terms. I know you really, really want to do 45 times 1/3 and then raise that to the power of n minus 1, but only 1/3 is being raised to the power of n minus 1. And according to order of operations, we always do exponents before we multiply. So this you actually cannot simplify any more than it's written here. So again, don't oversimplify because we cannot multiply these two terms. They don't have the same base, and this does have an exponent. So this is our explicit rule. So now let's work on our recursive rule. So our recursive rule, a sub n equals a sub n minus 1, which remember is just the term before, times our r value, which is 1/3. And in this case, we'll define our first term as 45, so we have a starting point. So this is our recursive rule. And now to find the 10th term, again, we'll go back to that explicit rule. So a sub 10 equals 45 times 1/3 to the power of 10 minus 1, which is 9. So remember, only 1/3 is being raised to the power of 9. So to help us simplify this, first I'll write it like this, over 3 to the power of 9. And I know that 45 is divisible by 9. So we have 5, which is 2 powers of 3. So divided by 3 to the power of 7. And then we can plug this number into our calculator. So we get 5 over 2,187. And there you have it. All right, at this point I'm going to ask you to pause the video and give this one a try on your own. All right, go ahead and check your work here. So we can see that our common ratio is 3 over 5. Let's look at your numerator. Your numerator is being multiplied by 3, and your denominator is being multiplied by 5. Again, if you're ever having trouble doing this, you could always take any term. So we'll take that second term, and you divide it by the previous term. So here we get 6 over 10, which is 3 over 5. So again, you can always do this to help you find that common ratio. Then we can see our first term is 2, so we plug it into our formula. And again, you cannot multiply these two terms because this term is being raised to the power of n minus 1, and the bases are not the same. Then here's our recursive rule, and then we'll use our explicit rule to help us find the 8th term, which is 4,374 over 78,125. All right, so now we're going to try to make explicit rules for our sequences given different information. So here we're told that the common ratio of a geometric sequence is -2. And we're told that the 6th term is -96. So here, what we know, so if we start using our formula, we know that our common ratio is 2. But we still need to know what the first term of our sequence is. So maybe rather than working our way backwards to find that first term, which we could do, it would just take us a little longer, we can use this to substitute into our formula to help us find a sub 1. So we'll replace n with 6, and we'll replace a sub n, the actual term, with -96. So we have -96 equals a sub 1 times 2 to the power of 5. So that means that a sub 1 is equal to -96 over 32. So that means our first term is -3. So from here, we can take this and substitute it back in to make our explicit rule. So it's negative 3 times 2 to the power of n minus 1. And please make sure that, again, we do not multiply these two numbers because they do not have the same base. So this is as simplified as we can get. And remember, for these, you can always check your work. You can plug in n with 6. You could substitute 6 for n and see if it produces negative 96 to make sure our rule is correct. All right, so go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. We can substitute n with 5 and a sub n with negative 5 over 1,296 to help us find a sub 1. We are given that common ratio of 1/6, and we end up with the first term being negative 5. So you plug that back in, and here's our explicit rule. All right, so now we're going to try creating an explicit rule for a geometric sequence given two terms within our sequence. So here we are told that a sub 6 is negative 15,552 and a sub 3 is negative 72. So we are missing both our common ratio and our first term. So we can set up a system of equations to do this. So for our first one, we're going to replace a sub n with negative 15,552 equals a sub 1 times r to the power of, instead of writing n minus 1, we'll replace 6 with n, so it's r to the power of 5. And then for the second piece of information, the term is negative 72 equals a sub 1 times r squared, because our n value is 3, so 3 minus 1 is 2. So for this, I think the best way to solve these is to use substitution. So I'm going to solve for a sub 1 for this first, or my second equation. You could do this for either way. And then I'm going to take this, and I'm going to substitute it into our first equation. So we get negative 72 over r squared times r to the 5th. And this we can simplify a little bit. So we get negative 72 r cubed. And then we'll divide by negative 72. So we get 216 equals r cubed. Remember, the way that we get rid of a cube is by taking the cube root of both sides, and the cube root of 216 is 6. So our common ratio is 6. Now that we have our common ratio, we can go back and substitute this into either of our original equations. So I'll go back and I'll substitute it up here. So negative 72 equals a sub 1 times 6 squared. And then we can solve for a sub 1. So we get a sub 1 equals negative 2. All right, so now we have everything we need to write our explicit rule. It's negative 2 times 6 to the power of n minus 1. Again, we can check our work by substituting n with 6 or 3 to make sure we get the correct term. All right, so go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. So you can see I set up my two equations, and I solved for a sub 1 and r using substitution. And that should give you this explicit rule, which again, you can always double check by plugging in 3 or 6 and seeing if you produce the correct terms. All right, so now we're going to try a couple of word problems that involve geometric sequences. So this says the population of a bacteria is initially 12,845 when a scientist discovers it. However, the population of the bacteria decreases by 1/3 each day. What will the population be after 2 weeks? So since we're decreasing by 1/3, that means that each day, each successive day, it is only 2/3 of what it was the day before. So you have to be really careful here. It'd be really easy for people to say that R equals 1/3. Well, it doesn't. And it would be really easy for people to say maybe R equals negative 1/3 because they think, oh, it's decreasing by 1/3. But again, it's maintaining 2/3 of its previous population. So in this case, R is 2/3. So you need to be really careful about that R value when you're working with these types of word problems. And then we also know that the initial population, so A sub 1, was 12,845. So from here, we can make our explicit rule. So A sub n equals 12,845 times 2/3 to the power of n minus 1. So we could use this to figure out the population of the bacteria after any given number of days. N, it would be the number of days. So if we want to answer the question, which is what will the population be after 2 weeks, we're going to replace n with 14. So remember, n is the number of days that has gone by. So we get 12,845 times 2/3 to the power of 13. And then this we can plug into our calculator. So when we plug this into our calculator, we get approximately, it's 66.0005. So since we're looking for the number of bacteria, it wouldn't really make sense to have a fraction of bacteria. So we'll just say that the population is 66 bacteria. All right, so here's the last one for you to try. So please pause the video and give it a go on your own. All right, go ahead and check your work here. So the important thing to check here would be our R value. That's usually the tricky part for these, is interpreting how to determine that R value. So if the number of infections increases by 25%, that means our R value is 1.25 because it maintains 100% of its value, which would be the 1 plus the additional 25, so 1.25. So just be aware if you had your R value as just equal to 0.25, that'd be a really common mistake. That you're saying that it's only 25% of what it was the previous day, which would actually be a decrease. So anytime you have an increase, our R value needs to be greater than 1. And then our A sub 1 is 15. So this is our explicit rule, which we could use to determine how many people are infected on any given day. And then our answer should be 9,694 people. And I rounded to the nearest whole person, so it doesn't make sense to have a fraction of a person. All right, that is all for today's video. Thank you so much for watching.